presented will be paper number 11. So it's time for the preparation of the reporter. Please write down your name on the clipboard.
升学没有那么强，真的要这样就去养培养，至少保送
大部分这个大概只有物理圈，
presentation of the recorder.
Okay, and hello everyone, my name is Georgia from Team Insulator, and today I'm going to talk about problem 11, pumping straw. And this is a problem statement. A simple water pump can be made using a straw shaped into a triangle and cut open at the vertices. And when such a triangle is partially immersed in water with one of its vertical and rotating around its vertical axis, and water may flow up through the float. And when you investigate the geometry and other relevant parameters affect the pumping speed. And in the right side of the videos, we can see that in the right side of the video, we can see that we let a straw in the water and rotate it, and you will through a throat and pumping out water. And you can see just like this picture. And along with the pumping out water, and the water level will drop, and the rotating speed will also increase. And the viscosity can support the water connect together, so the pumping out water shape of it will more like a droplet. And in this is about our observation that the pumping process, and we have a side view and top view. And in this sixth picture, we can see that if we let a rotating speed more faster, the pumping out will grow more higher, and the section area will get bigger. And you can see the next observation that when the water level lower than the straw, it can still pumping out water. And you can see in this videos, in this moment it started pumping out water, and it will again with the organized quickly. And we broke this process, and we use this. And in the first step, the water level is lower than the suction pipe inlet, and the straw keep rotating, and the water will float and pumping out the air. And the water surface is disturbed by the air current, and you want to cross in the middle and go up. And in enough height, you touch the straw inlet and pumping out. And you will go back to the step 4 and repeat it again and again. And this is a Venturi effect. It explains our observation that when the water level lower than the straw, it can still pumping out the water. And you can see in this picture it has a circle on it, and outside the straw, and you can see the area in here is larger, and inside the straw area in here is smaller. And you can imagine that because of we let the straw keep rotating, and the air will float. And we can know that when the air flow into the area is smaller, just like in the straw, the velocity will increase and the pressure will decrease. So in this picture, we can know the result is because of we let a straw keep rotating, and the pressure in here is different, and in a section of the air in it, and it will disturb the water surface. And water surface will want to connect in the middle and float up. And if we touch the pipe inlet in here, it can pump up. And in the video, we can see that it just pipe the water just a moment, and it's because we think the pressure difference is can against the gravity of the water. So it just pumping out a moment and the field level, and it will repeat it again and again. And this is our discussion of the process of accumulated water value of the angular velocity. And in this picture, we can see the left is the water level, and the right side is the angular velocity. And you can see around with the 40 seconds is about the water level is equal to the pipe inlet. And after the 40 seconds is about the water level is lower than the straw. And you can see in the end of this, it has a little up and down in here. And we think it's because of the Venturi effect. It's just, I said that it will pumping out water and again and again. And you can see in the angular velocity in here, it has a sudden pump down in here. I think it's because of it started pumping out water, and the water resistance was suddenly increase, and it will let the angular velocity decrease. And this is our first analysis. And in this picture, we assume along the thin line is fluctuating. and define the water is the opposite. And in this picture we can see there has a frost in here. And the green one is the normal frost, is N, and the blue one is gravity is about mg. And if we put gravity in here, we can get that is mg sin theta in here. And we also have the centrifugal force is the mr omega squared. And we broke the centrifugal force, we can get mr omega squared cosine theta. And we also has a chlorine frost in here. Because of we define the water is the opposite, so we need to add the chlorine frost to base this force analysis. And you can see the chlorine frost is about 2 times m times omega cross v. And because of our experiment, we let a straw like this direction to move. So the omega is here is to up in here. So omega cross v is about like this one. So the frost direction of the chlorine frost is into the paper. And in these two frost in here, we can now let the MA is equal to the mr omega squared cosine theta minus mg sin theta in here. And if it along with it, it means the force is to up and the water can pumping out. And this is the energy transfer. And we use the work in here is equal to the F delta S. And if we transfer in our force analysis, and we can equal to the this line about the mr omega squared cosine theta and minus the mg sin theta and times L. And it's my mistake that I didn't mark the L in here, but the L is length of it. So it's minus d cosine theta in here. And we also have kinetic energy in here, and we think in the work and energy is more equal. So if we let the load is 1, and we can know the equation that m is equal to the weight, and we can let omega we can let a formula like this. And this is the sum of pumping speed, and we can transfer in it, and we can get the v in here. And this is our experiment data. And we has a power motor, power spindle, and resistance. And we has a voltage in here, and we can see a left picture. We has a voltage increase, omega will increase. And I think it's because of this formula. And we can know that the voltage increase, omega in here will increase. So due to the energy conversion, when the voltage increases, the initial angular velocity will also increase. And the right side is about the pumping speed, and we can know that when the light is more close to the vertical, and it means the pumping speed will also increase. So you can see the trend is it, and the voltage increase, the pumping speed will increase. And it can combine in our this formula. You can see in this omega is increased and the V will also increase. So it means the pumping speed will increase, and it match our experiment data, the slope is increased. And this is our angular velocity in a different depth. And you can see in a horizontal line is about voltage. And just like I said that the voltage increase, the angular velocity also increase. So just that the last page said. And you can see the voltage line is about the inverse step. You can see when the inverse step increase, the angular velocity will decrease. And you can inverse that because of inverse step is increased, so the air resistance will increase. So it let angular velocity decrease. And this is our parameter of the angle. And you can see with change this theta angle in here. And you can see in the left picture, we have a trend of the angle increase, omega is decrease. And you can see in these two pictures, in this theta, we control these two sides is the same. So we can know that when we change theta and the radius in the straw will making a difference. So you can see in this formula, when the angle increase, the I in here will increase, and I in here is about the retention load, inertia in here, and we let a voltage in the same. So the I is equal to the omega mr squared. So I said that the R in here is different. So angle increase, the R in here is increased. So angle increase, the omega is decreased. And in the right side is about our pumping speed. And you can see the chart is the angle increase, the pumping speed will also decrease. And you can connect with our formula is like this. And you can see in formula R is increased and theta is increased and V also increased. And the pumping speed will also increase. And it matches our experiment data, the slope is increased. And the angular velocity in different depth, we can learn that just the last page I said that the horizontal line is the angle, and when angle increase, the pumping speed will also decrease. And the horizontal line and just the last parameter I said that it will decrease in this moment. And this is our parameter about the diameter in here. And we can see the diameter increase, omega will decrease. And you can see in that, and just like the I is equal to omega mr squared, and in this, because of the diameter is increased, so the m in here will also increase, and omega will decrease. And in here has a temporary action in here, and you can see in this formula, when the radius increase, the h is decreased, and it's connect with our real experiment. And you can see, and we can fix this plot in here. So you can see in this plot, the trend is the diameter increase, the pumping speed also increase, and it's connect with our formula, and the h is decreased or v is increased. And this angular velocity, and just that set as that. So in conclusion, we have the theory, and we use the work and the connected energies to calculate the V in here. And we have the parameter, we have the voltage and angle and diameter in here. And we can know the result is the voltage increase, the pumping speed will also increase. And the second one, the angle increase, the pumping speed will decrease. And the diameter increase, the pumping speed will also increase. And it's all connect with our formulas. And the important one is the key effect the pumping speed is the angular velocity. Thank you for attention.
So after that, please ask questions.
Okay, first of all, did you consider viscosity in the experiment?
No. In my post analysis, I said that the frequency.
Okay, and did you consider the pressure difference for the bottom and the power flow?
Yes, and you can see that in the better effect.
Okay, and these are very similar. What is the observer rate in your force diagram?
You said that.
Well, did you put your observer in the acceleration coordinate system? Yes or no?
Oh yes.
Okay. And turn to page 11. Then this graph on the left, linear correlation.
What?
The graph on the left.
The left.
Yeah, this is the linear correlation.
Yes.
Okay. And turn to page 13. And so the graph on the right, well, we have like a slope for each angle, right?
Yes.
And what does the slope mean?
Slow.
Is it a trend, or is it your vertical line, or
Can you point it?
and turn to the page before, turn to the page before, please. Yeah. So what is the straight line to do?
Straight line. You can just say that. This straight line is stress, and what about is stress?
The trend.
Oh, yes.
Operation of the opponents. The opponent takes the floor.
Okay, good afternoon. I'm the opponent from team PF5. My name is Ray, and we're going to abort the problem pumping straw. And this is a problem statement. And for the problem statement, their main focus is on the geometry and other relevant parameters that affect the pumping speed. And this is the overall summary of the report. So first of all, for the theory, they use the Venturi effect and the energy transfer of the water and the capillary action. And for the setup, they use a straw, a container, power supplier.
如果要用的话，就去接那个 reporter 的。
这个是时间。
哦，
因为它重启要一段时间，所以看你是要整还是要直接搬过去。
这台装的，不是这个，它接不过这儿的，那是这台装的。
那这样子就，但是他还是先让他 report。
不要换比较好，不要换，因为
等一下，
讨论的时候还是要看。
现在是在整这一台抽
要多
象，
久？是多久？
对吧？看你们要不要整。
多久啊？
大概
1分钟
这样。
1分钟就弄了，就让他 report。为什么突然没有？
哦，因为闲置太久。对，它有自动休眠功能，就一段时间没有就是输入讯号，它就会自己关机。
那现在是关机的时候。
它是关机，就是他们在一段时间，然后也没有在使用的时候。
几分钟后？
我自己体感是大概30分钟吧，30分钟没用，然后就。
休息时间要 test 一下就。
哦，这不是休息时间 test 的部分，这个是这个机器它自己的设计。
对，就也许可能。
休息的时候，
对，就大家
他们就先测试一下，它就不会中间太久没用。
刚刚中间有测试。
有，我们在休息的时间是有测试过的。
OK，好，还有怎样 ？Are you ready？
时间要重置吗？还是继续开始？
好，重置好了。
好。
Okay, good afternoon. I'm the opponent Ray from team PF5, and I'm going to develop the problem from this straw. And this is a problem statement. So the focus on this problem is the relation between rotating speed and the pumping speed, and angular velocity of straw variation during pumping process. And this is the overall summary of the reporter. So for a theory, they use the Venturi effect to describe the motion when the water is below the level of the straw. And they use energy transfer and capillary action. And the setup, they use a straw container and power supplier. And the parameters they change are the voltage, which changes the angular velocity, the diameter of the straw, and the elevation angle of the straw. And they're going to analyze the pumping speed. And for advantages, I think that they have great coherence and organization for their overall presentation, and a pretty clear explanation on this theory. And our suggestions, we think that they need clear expressions in graphs, and the relation between their data and theory, and other considerations for other forces. And these will be the points of discussion later. So first, I think I want to talk about the viscosity and friction, because I think that in some conditions it might affect a lot. And second, we want to talk about the pressure difference below the straw and below and on top of the straw. And also the linear correlation in voltage and angular velocity. We think that it doesn't fit the equations they have below. And then the slope of their data analysis. And I think that they need a clear expression on what the slope means and what the straight lines represent. And also at last, I think we need to talk about the definition of pumping speed. And we can start the discussion. And so, please turn to page 7 again. Okay, so you said that you didn't consider the viscosity, right?
Because in this plot, I will say as soon as the streamline is frequentist. So in this is just like yes, I didn't consider about the frequentist here.
And then why do you think you can neglect
And I
it?
think because I think I didn't use this, and it will let my theory and experiment has a different. So
So you're saying that you considered it before, but you think that it's different from your experiment data? And then you change it?
if we consider the fraction, and you will that is now the formula is you will have an error in it.
Then why aren't you explaining the error of your experimental data and instead of changing the theory? What is the meaning of doing this?
I think just you said that it has an error in here if we have a fraction, and I didn't consider that. And I think it's just in the error bar, it will show that the error in here. So it is why has the error bar in here.
So is this graph on the right your experimental data?
What?
Is the graph on the right showing the experimental data?
Explain data.
Yeah, then you said about the error, and I want to know where is your error bar.
And because of we just want to see the relationship between it.
Okay, it's fine.
Explain
So
the gravity. Explain gravity. What is gravity?
gravity.
Okay, come move on.
Okay, so what I want to ask is, are you saying that you considered the friction, the friction before in your theory, and then after you do your experiment, you found out that it has an error in the theory line in the data,
Yes.
and then you change it back into not considering friction.
And because of we think with the fraction in our formula, we can't count that it's curly. So we didn't consider that.
So you didn't consider friction because you can calculate its value.
It's more fancy, and I think we can use the simple line to let a chance to connect with our experiment data. And just you said the friction is the error bar to the short
Okay, so I don't really get what you mean, but I think it's fine. So maybe I have some misunderstandings about your answer, but I think that a better way to do this is not to change your theory line after you do your experiment, and try to interpret why is there an error in your data, and instead of just neglecting the friction to let it fit your data. Okay, so can you please turn to page 7 again? So where do you define your angle, the setup?
just here.
Oh yes, then
This is how angle.
then the centrifugal force on the axis of the straw, is it cosine theta?
Cosine. Yes, this is a cosine theta.
So, okay, so I think that there's a mistake in this expression.
Can you draw
I think
the
it's sine theta.
Can you draw that? I want to
Oh, okay,
check that.
Okay.
It's a
So theta is, you define theta. So this is the vertical axis. This is your stroke. And theta is this angle, right?
Oh yes.
And then you have the centrifugal force over here, which is like this. And you are going to get the magnitude from this direction.
Yes.
Yes, and
It's a cos. And the theta is a theta here. And I think it's a cos theta here.
I think that this is 90 degrees minus theta. Because this is a very, like this is not here, right? So then this is zero axis. So this is cos theta, right? This angle. This is also.
Oh yes, yes.
So then it will be that this angle is 90 degrees minus theta.
Oh yes.
Then the magnitude on this side should be this one times cosine 90 degrees minus theta, right? Is that true? Do you agree? Yeah, and this can be converted into sine theta, right?
I just don't get this which part of the angle to set.
No, well, this is not which part I said this. In your picture, you said that theta is this angle. Yeah, so from your picture, I think that this should be 90 degrees minus theta, right? Okay, then why do you think it's cosine theta? Okay, that's,
Sorry, that's running back.
yeah, okay, so you agree that this is
Yes, yes, and very angle that you pointed earlier.
and then can you please
So I think it's not affect our experiment results and
Oh, really?
didn't guess. And because of in our formula that just like an angle in here, it will both change the it just system in here and the angles also change. And I think the sin theta and cosine theta in here is my mistake. It's correct, but in this chart we think it is also a match our experiment data.
oh, so you think that changing that into sin theta will also match it?
Yes.
Well, but I think there's still some differences in cosine theta and sin theta, and
So
it's
you
not only
think-
slight differences. So I think that maybe you should still correct it and check it again. And it's okay. Then can you please turn to page 13, please? Oh yeah, it's so at the bottom right, you said that the pumping speed increases,
Yes.
and I want to ask you if the pumping speed is the speed over there, is it?
Pumping speed. Yes, and because of in our formula we let the pumping speed just is a speed.
So
And-
V is the velocity of the water when it pumps out, right?
Yes.
And what do you think pumping speed means?
Pumping speed means I think is the
Yeah, just use it.
I think the pumping speed is because of in our experiment we use the value of the water, so here.
Oh, okay. And just now you said that pumping speed is the speed over there.
I think yes,
Is it the same as
it's
this
a
one?
positive to this formula, and I think it's our experiment. It's our definition. And we use the formula to compute the. We use this rock formula and this formula to calculate to the V impaired.
So is this B over here the pumping speed that you define?
Yes, it's a pumping speed.
And is the pumping speed the same as the velocity of water when it goes out of the straw?
Yes, I think it's
Then how
positive
is
in
it?
here.
Okay, then how is this the same as the volume over time?
Of time. And you can and we can see that when just like the omega in here, and if the big increase, this means the energy times the graph is increased. So it's my
That's a bit
definition.
So what I'm asking is the definition of pumping speed. So what I think the definition of pumping speed should be the flow rate. So it should be the volume of water pumped out over time, just as you said, right?
Yes.
But you said that it's the velocity of water when coming out. So how is that the same thing?
No, I correct my opinion. I think this is correct.
You think this is incorrect?
Yes. In my opinion, I think this is my definition.
So the definition of pumping speed,
Yes.
then is that the pumping speed? Like the little b over there, is that the pumping speed?
Yes.
Yes, then.
Here is a little bit, and the big B is the water value.
Okay, so I think that you have a little misunderstanding of the velocity out of water pumping out and the flow rate. Flow rate is the volume over time. But the little b here is the velocity, or the unit of velocity.
Okay. Component summarize the discussion.
Oh, this is a summary of the discussion from the opponent. So, first of all, we think that friction and viscosity are important factors causing energy dissipation. And they said that they found that their data doesn't fit the theory line of their theory with friction, so they deleted friction. They chose to neglect friction in their theory. But we think they need a better way to explain why there's an error in their data. And the angle in their experiment and theory is wrong. So I think that they need to check their theory again to see if it really fits their experimental data. And as we talk about the definition of pumping speed, and they said that the definition of pumping speed is same to the velocity flowing out, the velocity of the water coming out. But we think that it is the volume of water pumped out over time.
Okay.
Thank you.
Question from the reviewer.
And just yes, and just that in our discussion text is just this. You must say the question is on the report. Can you repeat your definition of pumping speed?
The definition of pumping speed should be the volume of water pumped out over time.
Do you think surface tension equation? I think in my experiment, it can be it's very little and it can be.
Yeah, I think that affects but does not affect a lot.
And do you think that Bernoulli's law equation is? I think it's not important.
Can you say it louder?
Sorry. Do you think Bernoulli's law important in this experiment?
Yes, I do think so because it calculates the pressure difference.
And the equation measure the voltage. Do you think that's needed?
Well, I think that you are trying to say that the voltage is positively correlated to the rotating speed.
And the water level changes as the water is pumped out. Do you think that this should be fixed? The water level change, the water level change when the water was pumping out. Or it's observed in our experiment. Yes. Yes, and do you think you should because of this B is about the velocity. is immersed, so it's almost fits in our formula.
So do you think that the experiment setup should be fixed that water level should keep in the same height?
Well, it will not keep in the same height because water is pumped out, so the water level will go down.
And I want to ask, I want to say that in my experiment, we said that the initial immersed depth is the same. That's all my questions.
Preparation of the reviewer. Our reviewer takes the floor.
Hello everyone, I'm the reviewer from Century. And here's our problem statement, and we think the keyword in the problem statement is immersed in the water. So we think that the straw should be immersed in water. And we think the key points is the definition of pumping speed and viscosity.